So this will be our second video for aldehydes and ketones. In this video, we're going to talk about nucleophilic acyl addition reactions. So remember, aldehydes and ketones do not undergo nucleophilic acyl substitution reactions because there is no leaving group on an aldehyde or a ketone. You'd either have the hydride anion or you'd have some sort of carb anion. And those are not good leaving groups. They're too basic. So instead, we're going to react aldehydes and ketones with a variety of nucleophiles that are simply going to add to the carbonyl carbon. We're going to start by just sort of compartmentalizing these into different types of nucleophiles. And the first one I'm going to discuss will be the carbon-containing nucleophiles. A lot of these reactions are going to be familiar to you because we've used these nucleophiles before. We just haven't used them yet on an aldehyde or a ketone. But they act just like any other time they would be a nucleophile, right? They're going to have a source of electrons that are going to be used to attack an electrophilic atom on another molecule, and that will be the carbonyl carbon of the aldehyde or the ketone. So carbon-containing nucleophiles. The first example I have for you is a reaction with a Grignard reagent. Remember, you make a Grignard reagent with magnesium, right, in ether. So you take an alkyl halide and you allow it to react in ether with magnesium, raw magnesium turnings. The magnesium inserts itself between the carbon of the alkyl halide and the actual halogen. So you make an organomagnesium reagent. So this is an organometallic reaction. We're going to take our aldehyde or our ketone. Whoa, sorry about that. I'm going to take our aldehyde or ketone. I'm going to write it like this because it can happen to either. So R if it's a ketone, H if it's an aldehyde, right? And just generically, R prime, just to mean it could be a different R group. Magnesium and usually bromide. So this is our Grignard reagent. You can do this with other metals, but Grignard, the actual dude, did this with magnesium. So there's a whole ton of organometallic reagents out there, but an organomagnesium reagent is specifically called a Grignard reagent. We're going to take our aldehyde or our ketone. We're going to react it with our Grignard reagent. We're going to form our tetrahedral intermediate because these are going to react just like our carbonyl compounds with carboxylic acids and carboxylic acid derivatives, right? So remembering the Grignard reagent is going to react like R minus. Remember that? So it's like a carbanion. And so we're going to form our tetrahedral intermediate. So this is either going to be an aldehyde or a ketone. We have O minus up here. MgBr is going to coordinate with that just for a minute. And we end up with R minus adding. So this right here was the nucleophile. Only after we are satisfied that this reaction has occurred are we going to hit this with some acid. Because if you hit this with acid or any source of a proton, you kill your Grignard reagent, right? That thing's behaving like R minus, right? So it has like, in other words, it behaves like R with a lone pair of electrons and a negative charge. So a proton comes anywhere near that and your Grignard reagent is toast. So after you're convinced that this reaction has occurred between the Grignard reagent and the aldehyde or the ketone, we're going to do an acidic workup on this, and we're going to protonate the oxygen. So now, depending on whether or not you have an aldehyde or a ketone, you're going to get either a secondary or a tertiary alcohol. When formaldehyde reacts, you can get a primary alcohol, but any other alcohol where you have another R group, an alkyl group, you'll get a secondary alcohol. If you have a ketone, you'll get a tertiary alcohol. So formaldehyde, in other words, can react with a Grignard reagent. So this is normally, we put a little bond between that carbon and the magnesium. Sometimes it's easier to see written like that. This is going to attack the partially positive charged carbon, so our electrophilic piece of that functionality, form our tetrahedral intermediate. And then we're going to protonate this. And we're going to end up with a primary alcohol. If you want a primary alcohol, you need to use formaldehyde. Any other aldehyde, one of those hydrogens is going to be an R group, and so you'd end up with a secondary alcohol. So here we have a primary alcohol. We have another carbon-containing nucleophile, and that's the cyanide ion. So reactions with cyanide. We have a carbon triply bonded to a nitrogen, lone pair on each, negative charge on carbon. It is a carbon-containing nucleophile, so cyanide has a nucleophilic carbon that can add to an aldehyde or a ketone, and we create a new type of functionality called a cyanohydrin. These are pretty sensitive, so these steps are reversible, meaning if you're not careful, you'll end up with your aldehyde or your ketone back again. So this is going to attack the electrophilic portion of the ketone or aldehyde. We form our tetrahedral intermediate. And then we're going to protonate this with some acid. But notice all these steps are reversible. I assure you, these are annoyingly sensitive. And you can end up with your aldehyde or your ketone back again. if you're not careful. I ran one of these down a column one time to purify it when I was in grad school. I started out with an aldehyde, which is more reactive than a ketone, and I spent 10 hours purifying my cyanohydrin, and I got a sparkling clean aldehyde back again. Truly wasted, the worst waste of my time ever. So this right here is a cyanohydrin. So each one of these steps is going to be reversible. Cyanohydrins are pretty useful. They're useful as synthetic tethers or a synthetic group, right? Because we can do a ton of reactions with them to create new functionality. So I could take a cyanohydrin and react it under acidic conditions and get either a carboxylic acid, or I could get my aldehyde or ketone back again, depending on what your starting materials were. If I heated up the cyanohydrin under acidic conditions, aqueous acidic conditions, I can create a carboxylic acid. I can reduce them. I can do a catalytic hydrogenation to turn the carbon triple bond nitrogen into an amine. So there's a variety of different functional groups that we can actually get from that piece of functionality. So that makes that pretty useful for us. We have hydrogen containing nucleophiles. This will be kind of familiar because we already talked about the reverse reaction. So hydrogen containing nucleophiles, essentially reactions with the hydride anion, so H minus. So we have all kinds of sources of the hydride anion. Hydride H minus is very strongly basic. Remember, the pKa of hydrogen, molecular hydrogen, is somewhere around 40, which means that H minus is going to be a pretty wicked little base. So I can take either an aldehyde or a ketone, and I can react it with a source of H minus. We have a variety of those. Sodium borohydride is a pretty famous one. First step, this right here is our source of H minus. So in other words, you can look at this a couple of different ways. We have a hydrogen containing nucleophile, right, H minus, which is essentially going to share its electrons with the carbon of the carbonyl. So there's going to be a loss of electrons associated with the hydride anion. There will be a gain of electrons associated with the carbonyl carbon. So if you want to look at this from like a gen chem perspective, we have a redox reaction happening. In organic, when we're looking at reductions or oxidations, we're like, okay, if I reduce something, I'm basically increasing the number of carbon-hydrogen bonds. If I oxidize something, I'm increasing the number of carbon-oxygen bonds. You can also look at a reduction as a loss of carbon-oxygen bonds, right? So we're about to turn that aldehyde, or we should say, take that aldehyde carbon, and we're going to reduce its oxidation state. The second step for this is to protonate the oxygen, the negatively charged oxygen that is going to result. So we're going to add H minus to the carbon of the carbonyl, and then we're going to protonate the negatively charged oxygen. So this is just like any other nucleophilic addition reaction. So in other words, that will be there, and the source of H minus will go on the carbonyl carbon. If you take a ketone and you do the same reaction, you're still going to be doing a reduction, but you don't get a primary alcohol. You get a secondary alcohol. Remember, when you oxidize a primary alcohol under very specific conditions, you can get an aldehyde. If you take a secondary alcohol and oxidize it, you get a ketone. Tertiary alcohols cannot be oxidized. So I can use my source of H minus and attack the carbonyl carbon of the ketone. Hit this with some acid. And I have a secondary alcohol. What I've done is I have reduced the aldehyde to a primary alcohol, and I have reduced the ketone to a secondary alcohol. We have nitrogen-containing nucleophiles. Our celebrity nitrogen-containing nucleophiles are amines or ammonia derivatives. When we covered amines, we talked a little bit about some different functional groups that we can form using amines in carbonyl containing compounds. One of those was called an imine, and the other one was called an enamine. So we can do reactions with amines. If I take a ketone or an aldehyde and I allow it to react with a primary amine, I can form something called an imine, sometimes otherwise known as a Schiff base. If you work in a lab and you've heard somebody use that terminology, they're referring to an imine. Imines are compounds where you have a carbon-nitrogen double bond. The reaction is going to require a little trace, like a whiff of acid. Let me show you how this works, or how we think this works anyways. I can take an aldehyde and a primary amine, and under acidic conditions, I can create something called an imine. So now instead of the carbon double bond oxygen, I have a carbon double bond nitrogen, and that nitrogen has its R group. This thing is an imine. We have a primary amine, that's important. We'll form something else with a secondary amine. And it can be either an aldehyde or a ketone. So if that H was an R, for example, then it would be present in the product. But the star of the show here is the carbon double bond nitrogen. And that nitrogen will have its R group. So how does this work? Let me show you with, I guess we could do this with a ketone. Our generic example is done with an aldehyde. So I can take cyclohexanone, and I can allow this to be attacked by a primary amine. This is my nitrogen-containing nucleophile. See the lone pair of electrons on the nitrogen? I'm going to use those to attack my electrophilic carbon. And I'm going to shove the electron density up onto the oxygen. So over here, I have my negatively charged oxygen. Over here, I have my positively charged nitrogen after the attack happens, right? This is going to be done with a trace of acid. So now this, you can do this without acid. It just takes forever. Probably, shuffling protons around the molecule so that oxygen can probably snag a hydrogen off of the nitrogen, whatever. It just goes a lot faster if you put a little drop of acid in here. So what I can do is draw this like this. There's your drop of acid. And we're going to protonate that oxygen. What I'm trying to do is create a decent leaving group. Because notice how there's no oxygen in my imine, right? So again, notice how we're going through these different tetrahedral intermediates. I got a protonated tetrahedral intermediate coming up over here where I've got a nitrogen with a positive charge. I have protonated the oxygen. It's on its way to being a decent leaving group. We're not done with it yet. But this will be your first tetrahedral intermediate. We talked about these in the carboxylic acid stuff. You have your first tetrahedral intermediate. It's protonated. You got water floating around now. I'm going to deprotonate the nitrogen. I have the neutral tetrahedral intermediate. Remember, you get that as the second one. We have acid back because we just used the water to deprotonate the nitrogen. See, we have our little positive charge there. So this oxygen is going to grab a proton and get the third tetrahedral intermediate, which is also protonated, but now I have a better leaving group, don't I? I've got water. These electrons are going to come down. I'm going to form a carbon-nitrogen double bond. Water is going to split. So again, that's the third tetrahedral intermediate. 1 and 3 are charged. Under acidic conditions, they're positively charged. The second tetrahedral intermediate is neutral. Water is going to come back and it's going to take the hydrogen off of the nitrogen. And I have my imine. And I got the acid back. This is an imine. Notice how it has carbon-nitrogen double bond. Nitrogen has its alkyl group, or its R group, whatever. So with primary amines, with aldehydes and ketones, we can form something called an imine. If I take a secondary amine, so I can take a ketone or an aldehyde. And I can react this with a secondary amine instead of a primary amine. I don't get an imine, I get something else. Again, with a whiff of acid. Should probably put a methylene in the middle here. Just to make it a little easier to see. I don't get an imine here, I get something called an enamine. Notice how we don't have, with the secondary amine, I don't have the proton like I did, the extra proton, like I had with the primary amine. Notice how in that last step, or like one of the last steps, we've removed that hydrogen from the nitrogen. Water is not coming by and taking a methyl group off that nitrogen. What it can do is it can take a hydrogen off of an adjacent carbon. So we get something different. We get something called an enamine, which we can absolutely do further chemistry on. The mechanism is sort of similar to that of the imine formation, right? So similar to the imine formation, we're going to attack with the amine. Here's my secondary amine. I'm going to attack the carbonyl, carbon. Get my tetrahedral intermediate. Nitrogen has a positive charge. The oxygen has a negative charge. We get a little bit of acid in the flask. I'm going to protonate the oxygen. So this is all same old, right? So there's that protonated tetrahedral intermediate that we were calling before number 1. Water can come by, grab that hydrogen, return the electron density to the nitrogen. And now we have acid in the flask again. We can protonate the oxygen. Create our good leaving group. And then what ends up happening, we think, is you could have this double bond form. This leaves, but then you get you get essentially, I'm going to flip this around so that it's easier to see. this species where if we were, so see how there's no hydrogen on the on the nitrogen to take off. We got water floating around, but I can draw our hydrogen on the next door neighbor carbon. If we take this off, these electrons come up here. We form a double bond between the two carbons and push electron density back to the nitrogen. And you get your acid back again. This is going to be your enamine. It's ene for the double bond and amine for the nitrogen with the R2 or whatever your, alkyl groups are. So your secondary amine can attack an aldehyde or a ketone and form an enamine. A primary amine will form what's called an imine. Now we've got our last nucleophile category, our oxygen-containing nucleophiles. So just like with the nitrogen-containing nucleophiles, where we're forming a new piece of functionality, new name for us, an imine. So that's just a general name, right? That particular molecule has a name. It is called an imine, though. Like, there's a lot of imines out there. The general feature is a carbon nitrogen double bond, right? Where the nitrogen has its alkyl groups, carbon has its alkyl groups, right? That's an imine. The enamine, again, is not just that particular enamine, but it could be any molecule where you have a carbon-carbon double bond, and then one of the carbons is bonded to an amino group. That's an enamine. We're going to create some new types of functionality, and I'm sure that I'm not sure, but I'm betting that some of you have heard of these before if you've taken any nutrition or biochem type classes at all. We're going to do some reactions with alcohols. So the product that we're going to form, well, first we need to focus on how many equivalents, stoichiometric equivalents, like in other words, how many moles of alcohol we're going to use to react with either an aldehyde or a ketone, because it's going to make a difference for the product that we get to form. Alcohols are kind of crappy nucleophiles, right? They're neutral. So we're going to need to use some kind of a catalyst. And usually we use an acid catalyst for these reactions. In other words, I mean, I guess you could say that this reaction would go, but it's going to go at the speed of a snail, and all the steps are reversible. So the more stable species is going to be probably staring at you as unreacted reactants at the end of the day. So we get this thing to plow forward with an excess of the alcohol if we're forming what we call an acetal or a ketal, or stoichiometrically one equivalent of alcohol if we want to form half of an acetal, in other words, a hemiacetal or a hemiketal, and just a trace amount, a couple drops of some acid catalyst. Again, alcohols like water are poor nucleophiles, right? They're neutral molecules. So if I take my aldehyde and I allow it to be protonated with acid, what am I doing? I am creating a better electrophile by putting a positive charge on the oxygen. The carbon is hotter for nucleophilic attack. We talked about this when we did carboxylic acid derivative chemistry, right? We're going to take one single equivalent So this is all theoretical, right? One equivalent stoichiometrically of alcohol. And we're going to attack our protonated carbonyl. Again, we see these tetrahedral intermediates form. This oxygen still has its hydrogen. Because we used acid, right? So we had the hydronium ion in there. We have some water floating around. And we can deprotonate that oxygen and give the electrons back to the oxygen and form something called a hemiacetal. This right here. Hemi means half. This is half of an acetal. You could do the same reaction with a ketone. The difference would be there wouldn't be a hydrogen there, there'd be an R group there. If that was done with a ketone, it would be called a hemiketal. So in other words, you can do the same thing with a ketone. I'm going to protonate the oxygen of the carbonyl. This makes this carbon more susceptible to being attacked by a nucleophile, because alcohols are not the best nucleophiles. They're kind of weak, right? I take one equivalent of alcohol, and I'm saying one equivalent pretty specifically because I'm going to show you what happens when we add two. And I form my tetrahedron. This is all the same thing we just saw, right? With the aldehyde. Only this time, we started with a ketone, so that H is actually an R. Water is going to come in. This is probably from your acid solution. Notice this carbon went from sp2 to sp3. Instead of a hemiacetal now, we have a hemiketal. If I was going to add another equivalent of alcohol, so I'm going to take my hemiacetal. So this right here, I'm going to start with this. If I were to add two equivalents of alcohol, what I would have is the hemiacetal, or I could do this with the hemiketal. I'm just going to grab one of them, right, because the chemistry is the same. So I'm going to bring that down here. Remember, these tetrahedral intermediates, this is the same old pattern, right? You start out with your first tetrahedral intermediate, it is protonated. You get your second tetrahedral intermediate, it is neutral. You get your third tetrahedral intermediate, it is protonated. Your second neutral, right, your neutral tetrahedral intermediate, in this case, has a name, and it's called a hemiacetal. So I'm going to put that down here. And if I had another equivalent of alcohol, I can continue this reaction, can't I? So I still have acid floating around in the flask. So this reaction can continue as long as I have alcohol present. All of these steps are reversible. There's that third tetrahedral intermediate technically, right? So the first one had the positive charge, the second one is neutral, the third one has a positive charge. It's our second one just happens to have a name. It's a hemiacetal. In this case, water is going to be eliminated. I'm going to flip this upside down. A little easier to see. Doesn't that look an awful lot like a protonated carbonyl? It's not protonated, though. It's alkylated, right? The oxygen has an R group on it instead of a proton. But still, now that carbon is hotter for nucleophilic attack. If I have a second equivalent of alcohol, it can come in and attack the carbonyl carbon. And it's the same old stuff, right? Water is then going to come in, take its proton back, well, the hydronium ion, take its proton back. Water will deprotonate the oxygen. And notice the difference between the hemiacetal and this new thing we're going to form. This thing is called an acetal. So instead of a hemiacetal, notice how the hemiacetal has an OR and an OH. In the acetal, that OH is an OR. So I've got two alkoxy groups on my now sp3 hybridized carbon. In the hemiacetal, I had a hydroxyl group and an alkoxy group. So if we do this with a ketone, some books will actually call both of these an acetal and a hemiacetal, and some books will actually differentiate between a hemiketal and a hemiacetal. The way that the way that you can tell the difference is that if it came from an aldehyde, you have a hydrogen there. If it came from a ketone, you'll have an R group there. This makes it super easy to tell because I'm just using R and H, right? So it's not too difficult to see the difference between the hemiacetal and the hemiketal. When you get into like natural products where we find these hemiacetals or full-on acetals or ketals or whatever naturally occurring, it's a little more difficult. It can be just a little, especially if they're part of a ring, it can be difficult to see what the R piece is. Carbohydrates are famous for forming these things. So let me show you an example, a specific example. We'll say a specific sort of celebrity example. Of acetals or hemiacetals. So, and also their ketal versions. So specific examples of these will be carbohydrates. I can have my sugar, I can have a monosaccharide like D-glucose in its open chain form. So for example, I could have D-glucose draw this out for you. So glucose is an aldehyde in its open chain form. It's a hexose, so there are 6 of these carbons. When we draw the open chain form, just to make it a little easier, we draw these sugars, these carbohydrates, in their open chain form like a Fisher projection. So for D-glucose, I've got this one turned around. Sorry, this is just how I remember them. And I want to show you what happens when we take this. Now, in these examples, what I showed you was an alcohol coming in, right? This alcohol comes in as a nucleophile and attacks the carbonyl carbon. This is going to be, so that's an intermolecular reaction. This is going to be an intramolecular reaction. I have got the nucleophile and the electrophile all built into the same molecule. So, and this won't be the last time we see something like this happening. I'm going to take that hydroxyl group and that carbon, and we're going to attack. And I'll do this in a different color. It's a little easier to follow. So imagine that this thing attacks that carbon, just like it would if it was a separate alcohol, right? I'm just attacking to form a 6-membered ring. My 6-membered ring, sometimes we draw it like this. So this is under enzymatic control, right? So we have a little, I'm just going to throw that freebie proton on there. So sometimes you might see it written like this. Oops, let me put the bond in. Sometimes in like a nutrition or a biochem textbook, very often they'll do that. This thing right here is our hemiacetal linkage. So sometimes you'll see it written like that. So there's your carbon, right? Just like any other hemiacetal. The whole rest of this thing is R, right? This is one of the hydroxyl groups. This and the rest of this crap is OR, like the whole rest of the molecule, right? And then it came from an aldehyde. So there's a hydrogen there. So when I say sometimes it's easy to see, and sometimes like up here where we're looking at a hemiacetal, we have that carbon, we have an OR, we have R on the carbon, right? And then we have a hydroxyl group and a hydrogen. We have the same thing going on down here. It's just a little harder to see. The rest of the ring is both R and R prime, in other words. So I can draw it like this, just to make it a little more obvious. I'm going to not draw the stereochemistry in because it's not really the point here. So there's the carbon. There is a hydrogen sort of implied there, so it came from an aldehyde, right? We've got the hydroxyl group. We have O, R, so that whole rest of the ring is R. And then on the other side of the carbon, there's an R group, but it happens to also be the rest of the ring. So sometimes these can be hiding. If this was a a hemiketal, then there would have been, instead of a hydrogen on that carbon, there would have been a another R group. Fructose, for example, forms a hemiketal. So there would be another methylene with a hydroxyl group. So fructose is actually a ketone. They both have 6 carbons. The fructose will form a 5-membered ring. Glucose will form a 6-membered ring. You can get a ketal, a full-on ketal, if you hook up, say, a unit of glucose with fructose. So you'll have an acetal linkage and a ketal linkage. In carbohydrate chemistry, we call those glycosidic bonds. So when you're reacting an aldehyde or a ketone with one equivalent of alcohol, so up here I'll put 1 stoichiometric equivalent of the alcohol will give you a hemiacetal or a hemiketal. 2 equivalents of alcohol with an aldehyde or a ketone, and you'll get a full-on acetal or a full-on ketal.